Hi everyone. I'm Peter, and there's Igor that's presenting with me today. We're going to talk about MSRF Net. It's a multi-scale residual fusion network for biomedical image segmentation. A very fancy name, but in reality, it's just a neural net that segments various things in biomedical images, and looks like pretty much all of the images. If we take a look at the list of authors, we can already see that all of them are members of IEEE, and none of them are really have any. None of them seem to have medical expertise or any sort of biomedical credential right off the bat, which actually is going to come in important later in this paper. But yeah, so the problem is to improve the performance of biomedical image segmentation. As we can see, we have a bunch of lesions here, and cell nuclei right here, and some skin cancer, and there is some ground truth that has an expert has selected. And essentially what they're trying to do, they're trying to have the neural net produce the same kind of a mask. And this particular neural net is doing fairly well. They have a few data sets that they're going to use. And yeah, so let's see how this thing actually works. Igor?
Yeah, and right here you can see the architecture of our MSRF net. And it's pretty sophisticated. So first we have encoder layer. We'll talk about it a little bit later. Then MSRF subnetwork, which goes to the shape stream block. And after that, the decoder block takes something from the shape stream block, and the MSRF subnetwork process it and gives us a result. So basically this architecture based on the encoder decoder kind of stuff, and encoder and decoder consists of multiple mechanisms that we talked about later. And one crucial thing is that we'll talk about that at the end, but we can definitely remove some of these blocks, some of this part of the code, and the model in some cases perform as good as with all the blocks here. We can see this in the metrics in the end. And on the right side, you can see the decoder net block. It's also pretty sophisticated with a lot of layers, but most of them, and this decoder part is based on the convolutional layers mostly. Yeah, that's it. Let's go to the next slide. Yeah, so here you can see the dual scale dense fusion block, which and actually works with high resolution and low resolution images. So first block on the top, you can see that takes high resolution images XH, and block on the bottom takes XL, so low resolution features, and process it. One interesting moment here is skip connections, which actually responsible for this fusion. So it produces diffused feature maps that allows us to have the multi-resolution output eventually. All right, can you please go next? Yeah, and the MSRF subnetwork, you probably remember from our previous slides, the architecture of the entire MSRF consists of this MSRF subnetwork that just take a bunch of DSDF blocks and output the multi-resolution features to us at the end.
Cool. Let's talk about the data set that they used for this. They've essentially they claim that they used 4 data sets: Quasir Seg, CVC Clinic DB 2018 Data Science Bowl, and ISIC 2018 Challenge. So Quasir Seg essentially has a lot of various images of tumors and other lesions. And CVC Cleaning DB has it's a fairly similar data set at least, but the image size is not variable. It's they're all the same. 2018 Data Science Bowl primarily has cell nuclei just stained, so just like little red marks as you have probably seen over here. Yeah, this image is generally a pretty good description of the data set. So yeah, Kaggle Data Science Bowl has like these red marks, and then ISIC 2018 has yeah, images of skin cancer, so and various skin damage. So yeah, that's what the data set looks like. And they essentially they train the model on Quasir seg and a CC seg, and as you can see, they've used a 80-10-10 train validation test split. The data sets are not very large, so they applied some data augmentation techniques that we're gonna talk about later. Yeah, so yeah, as far as
Yeah,
implementation goes.
regarding the implementation details, the most interesting here is that we have all the images was resized is the first, and also you can see the different batch sizes for different data sets with different image size was applied. So we have also 200 epochs and yeah. Regarding the data augmentation techniques, yeah, we'll talk about that on the next slide. So please, yeah.
Yeah, so the pretty standard data augmentation techniques have been used in this particular work. Specifically, they mention random cropping, random rotation, horizontal flipping, vertical flipping, and grid distortion, right? But the question is, my personal question is that, is it a valid thing to do in the medical field? Is it a valid thing to actually apply distortion to biomedical images, or is it going to damage the cause? But anyway, so let's talk about the evaluation metrics for this model. They use dice coefficient, they use mean intersection over union, they use recall, and they used precision. Also frames per second, pretty good metric. But I don't really know what dice coefficient is or mean intersection over union. But we'll try to yeah. So we did a little bit of research, and we're going to tell you right now. So dice coefficient is it's a statistic used to evaluate the similarity of two samples. And essentially, we can take two images and like overlap them like this, kind of like two livers right here, so you can see. And then if we take their area and the area of their overlap of their intersection, right? And we use this formula, we're going to get the dice coefficient and mean intersection over union, right? So we have the original image, and then we have our ground truth, and then we have what the model has segmented, and we overlay them, and we divide the area that's over here, right? The white area over the area of the whole thing, and that's going to be our mean intersection over union. Very interesting metrics, especially when it comes to like image segmentation. Cool thing to remember.
Okay, and briefly regarding loss computation, so we have simple binary cross entropy loss, and yeah, something that called dice loss. You can see on formulas 8 and 9. And on the bottom, the final loss function that represented as a sum of different loss functions just tells us that different losses was applied to different part of our architecture of MSRF Net.
Yeah. So, well, let's talk about the results of this particular model. As we can see, well, when it's trained on, and Zoom's getting in the way over here. So, yeah. So if it's trained on the Quasir data set and also tested on the Quasir data set. So, yeah, if we look at the results, I mean, the reality is they did get like a score improvement, but it's about like it's about like 2%. It's between 2 and 4% when the average score is about like 90%. So not a very super extreme fantastic improvement, but it does outperform all the models out there. And the frame per second rate actually makes it very viable to use in real time. And pretty much the same thing happens on when it's trained on the CVC Clinic DB data set. Yeah, score improvement by about 0.4 by about 4% at 90 plus. So score improvement, but yeah, yeah, still pretty good FPS. Performs fairly well. However, what's interesting is whether these results are generalizable. So can we like train this neural net on one data set and then like test it on the other? These results are like less exciting a little bit, maybe at least when it's trained on Quasir Seg. Because Quasir Seg is a fairly tough data set, much tougher than like CVC, for example, or the other two data sets, because the other two data sets are actually fairly easy. But yeah, if we're looking at a bunch of like cancerous tumors, the scores drop, but the authors still consider them acceptable. The worst thing that happens, precision drops by like 10%. Right. And if we train it on the CVC Clinic DB data set, the score falls only like, DSC and mean intersectional reunion is pretty good. But the recall falls about 8% and precision falls about 1%, which is pretty good. So we can generally conclude that the CVC trained model is fairly generalizable. And they also performed the thing called ablation study. And ablation studies, that's something that I've never heard about before. So I'll talk a little bit about that. Ablation study is when you take your model and see what features are important and what features are not important by removing them from the model. In this particular scenario, the model has been they were taking the model apart using by pulling out some of the layers out of it. I'm sorry, I'm lagging. Yeah, so the quick result that we can conclude out of this table, like right away, we can speed the model up twice. We can make the model process double the amount of frames that it could before if we just remove the subnetwork, but that is going to come at the cost of 5 to 7% accuracy pretty much on every metric out there. So yeah, that's our presentation. Thank you very much.
Thank you, everyone. Yeah, please feel free to ask any questions.
Well, I don't hear any questions. Pleasure talking to everyone. Thank you guys. Have a great day. See y'all at demos tomorrow.
See you, everyone. Bye bye.